नमस्ते दोस्तों। तो आज एक्चुअल में कोई फॉर्मल पढ़ाई की नहीं बात करेंगे। आज हम पढ़ेंगे फिजिक्स का सबसे अनोखा ब्रांच, जिसको क्लासिकल रियलिटी से थोड़ा हटके क्वांटम मैकेनिक्स का एक स्पेशल इवेंट के बारे में, जिसको हम बोलते हैं टनलिंग, द क्वांटम टनलिंग इफेक्ट। क्वांटम टनलिंग इफेक्ट पढ़ने से पहले एक स्टोरी को समझते हैं। स्टोरी कुछ ऐसा है, मान लो एक पहाड़ है और जिस पहाड़ का कुछ हाइट तुम्हारा जहां पर h मीटर है, राइट। h मीटर जो हाइट है, उस हाइट में एक पहाड़ है। अब उस पहाड़ का तुमको क्या करना है, वो पहाड़ को जहां से मान लो ये बॉल है, उस बॉल को एक वेलोसिटी से मैं पुश कर रहा हूं, पर एक ऐसा वेलोसिटी देना पड़ेगा ताकि ये इस पॉइंट पे आ जाए, करेक्ट। अब जहां पे मान लो वेलोसिटी देना है, तो इसमें काइनेटिक एनर्जी आएगा हाफ mv स्क्वायर। इनिशियली इस लेवल का हम जीरो मान रहे हैं, जहां पर कोई पोटेंशियल एनर्जी नहीं है। दिस इज द काइनेटिक एनर्जी, राइट, एट दिस पॉइंट। और जब इस पॉइंट में उठ जाएगा तब mgh प्लस कुछ ना कुछ वेलोसिटी हो जाएगा हाफ m। मान लो इस पॉइंट पे आके इस बॉल का वेलोसिटी समथिंग v नॉट हो गया। अब तुम क्या जहां से क्या लिख सकते हो, हाफ m इंटू v नॉट स्क्वायर equal to half mv square minus of mgh, and it should be greater than equal to 0 because half mv naught square kinetic energy is a positive quantity. We all know that. So from this relation we can get that v square greater than 2gh, so v greater than equal to square root of 2gh. So the minimum velocity that I should apply to cross the barrier to climb the mountain is minimum velocity is square root of 2gh, because when the ball reach this point, it will go down with the use of the gravity. The gravity will pull it back. Okay, so it will automatically reach this point. So we have to project a minimum velocity of square root of 2gh such that it can climb the mountain. Okay, now this is known as the classical mechanics. This is usage of the conservation of energy. Right, so this is uses of the conservation of energy. Now, is there any way such that we can pass the ball from the point A to the point B without climbing? ऐसा कोई तरीका है कि हम बिना क्लाइंब करे इस A पॉइंट से B पॉइंट में पहुंच जाएंगे? अब बहुत लोग बोलेंगे सर गड्ढा कर दो, यहां से गड्ढा कर दो, गड्ढा करके पहुंचा देंगे, पहाड़ के अंदर खोद दो, टनल बना दो। यही चीज होता है क्लासिकल मैकेनिक्स में। अब मान लो तुमने जो मिनिमम स्क्वायर रूट ऑफ 2g वेलोसिटी देने की जरूरत थी, अगर ये टनल होता इतना देने की जरूरत होता नहीं होता है, इतना देने की जरूरत नहीं होता। अगर टनल होता, उस टनल में थ्रू पार कर देते, वो सीधा सीधा बॉल ऐसे 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 करके आ जाता, राइट। और ये हाइट मान लो बहुत ही कम है, इट इज h नॉट एंड इज वेरी मच लेस हाइट, तो इतना मतलब वेलोसिटी देने की जरूरत ही नहीं था। पर जब टनलिंग रहेगा तब ना, पर प्रैक्टिकली ये पॉसिबल नहीं है। अगर वेलोसिटी इस वेलोसिटी से कम हो गया तो ये रीच नहीं कर पाएगा। तो अब क्वांटम मैकेनिक्स में इन द क्वांटम टनलिंग इफेक्ट एक्चुअल में होता क्या है? एक्चुअल में क्वांटम टनलिंग इफेक्ट में क्या होता है, अगर इस बॉल को तुम एक इलेक्ट्रॉन इमेजिन कर लो, एक बॉल को इलेक्ट्रॉन इमेजिन कर लो, वो इलेक्ट्रॉन इन क्वांटम मैकेनिक्स क्या करता है, वो एक्चुअल में टनलिंग कर पाता है। मतलब इस ए पॉइंट से बी पॉइंट वो टनल के थ्रू जा सकता है। अगर मान लो ये तो मिनिमम कंडीशन है। अगर मान लो इसमें ऐसा हो जाता है कि v इज लेस देन इक्वल टू स्क्वायर रूट 2gh, मैं लेस देन इक्वल टू नहीं लिख रहा हूं, ये इस दैट इंप्लाइज द टोटल एनर्जी इज लेस देन द पोटेंशियल एनर्जी। The total energy is less than potential energy. That means kinetic energy is less than 0. This is the total energy, right? And it is the v naught plus t. So if E less than v naught, the kinetic energy is less than 0, which is actually impossible in the classical mechanics. तो ये बात है कि जहां पर रीजन क्लासिकली फॉरवर्ड है, वहां पर क्वांटम मैकेनिक्स में वो अलाउड रीजन है, क्योंकि E लेस देन v नॉट इसी कंडीशन में टनलिंग देखा जाता है क्वांटम मैकेनिक्स में। इलेक्ट्रॉन इस कंडीशन में भी पार कर सकते हैं किसी भी बैरियर को, तो इसको एक्चुअल में टनलिंग इफेक्ट बोलते हैं। कि जो रीजन क्लासिकली फॉरबिडन है, जो रीजन हमारा क्या है, क्लासिकली फॉरबिडन है, क्लासिकली फॉरबिडन है, इसका मतलब E लेस देन वी नॉट वाला रीजन। जैसे मान लो जहां पर कोई मैंने अगर ग्राफ ड्रॉ कर दिया V वर्सेस X का, और मान लो तुम्हारा ग्राफ कुछ ऐसा है और तुम्हारा टोटल एनर्जी कुछ मान लो इसमें है E, तो इस पार्टिकल इन दोनों के बीच एक्चुअल में रहेगा, ये एक रिटर्निंग पॉइंट दोनों रहेगा, है ना, ये एक तुम्हारा A पॉइंट और ये एक तुम्हारा B पॉइंट। ए और बी में पार्टिकल का ऐसा छोड़ के रख दे कि जहां पर पहुंच गया इतना ऊपर पहुंच नहीं पाया, तो जहां से ये पार्टिकल नीचे आ जाएगा, फिर से किया तो फिर से ऊपर उठ जाएगा। तो ऐसे होता है, ये जैसे मान लो E और इसके ऊपर पार्टिकल नहीं जा पाएगा, इसके और इसके ए और बी पॉइंट के बीच में ही रहेगा, तो ये बाउंडेड रीजन के अंदर E लेस देन V नॉट क्लासिकली फॉरबिडन, बट इन क्वांटम मैकेनिक्स इन थ्रू टनलिंग the electrons can go through this barrier. There is some probability in the other side of the barrier. In the classical mechanics, there is no probability. If this is the condition, there is no probability of finding the particle in this region. But in quantum mechanics, due to the tunneling effect, there is some probability to find the particle in the B side also. This is known as the quantum tunneling effect. Now, what is the application? The best application is astrophysics and in nuclear physics. In nuclear physics, we all know about the sun's radiation. Okay, the sun's radiation. How this sun's radiation come? Because of nuclear fusion. And this nuclear fusion happens through 1H2 plus 1H3. It releases 2He4. So deuterium plus tritium gives us helium through nuclear fusion. But what is fusion reaction? The protons should come closer to each other, right? In the nucleus there is proton. So during the nuclear fusion process in the sun, the protons should come close to each other, but there is a columbic repulsive force because they are like charges. So like charges repel each other, so there should be columbic repulsive forces. So to overcome this columbic repulsive behavior, columbic repulsive barrier, to overcome this barrier, we should give the proton sufficient energy. But the stellar, the core part of the sun, the temperature of the core part of the sun, which is about 10 megakelvin, is not sufficient to give the energy to the proton to overcome this columbic behavior. In this case, the proton shows the tunneling effect to overcome this columbic barrier. There is a repulsion in between the protons because they are like charges. So to overcome this columbic barrier, the protons shows the tunneling behavior. It is in the application of the nuclear fusion process. So we can discuss it in detail in nuclear physics. And this tunneling effect is also the main reason of Hawking radiation through the black hole. It is all about astrophysics. And there is STM. Okay, so it is a tunneling scanning microscope. Scanning tunneling microscope. This is STM, known as STM. Another is tunnel diode. Tunnel diode. Okay, the diode are doped 1,000 times more than normal doping. Okay, such that the depletion layer is so small, so the electron can tunnel so easily. Another application is Josephson effect. Josephson effect. So it is actually the electron tunnels through an insulator. Okay. And this insulating layer is made by cutting pieces of superconductors. Okay, so this is known as Josephson effect. There are so many applications of this tunnel effect. Now go through the actual quantum mechanics tunneling effect. So the region which is classically forbidden, but there is some probability of finding the particle quantum mechanically. This is known as the classical mechanics forbidden region. So first of all, we actually draw the diagram of the tunneling. What is the diagram of the tunneling effect? It is actually like a step potential. This is the V, this is region 1, we consider this is region 2, and this is region 3. This is the potential axis, V as a function of X, this is X, and this is a constant potential here. So we actually, and this is X equal to 0 to this X equal to L. For region 1, for the region 1, For the region 1, we will mathematically see by applying the Schrodinger equations. Actually, does any probability exist in the region 3? Okay. So in the region 1, there is no potential. In the region 3, there is no potential. For region 1, what is the Schrodinger equation? H square by 2m. Del square xi as a function of x upon del x square. Plus, this is potentially 0 in this region. So this is B0. And E as a function of, E into xi as a function of x. So we can write that del square xi as a function of x square upon del x square equal to minus of 2me upon of h cut square of xi as a function of x, right? So now we can let that is alpha square. We can let alpha square equal to 2me upon h cut square, right? So we can write the equation of del square xi upon del x square equal to minus of alpha square xi of x. From this, the xi of x comes a cos alpha x plus b sine of alpha x. Oh, okay. There is another solution also. So from this, that d equal to plus minus I of alpha, right? Because d square by dx square is known as d square. This is minus alpha square. So d equal to plus minus alpha. So a to the power I alpha x plus b to the power minus of I alpha x. Okay. Now it is xi of the first region of x. So a e to the power x is actually how it looks like. This is region 1, right? This is region 1. How it actually looks like, there is a way going through this. This is actually a e to the power I alpha x. The particle which is reflected, it is known as d to the power minus of I alpha x. And there is a transition and there is a decaying. We will see every positions. So this is reflecting, this is actually incident, right? Xi 1 of x. So this is reflecting, this is known as actually incident. This is incident, right? And this is known as the reflecting. This is known as incident, this is known as reflecting, right? So we need this equation, xi 1 of x, and nothing more than that. So just note it down. Take a screenshot or note it down. Okay, this is known as I1 of x. So we have incident wave which is the reflected wave, right? And for also region 3, the potential is also 0. So in the region 3, we can simultaneously say there is some f e to the power I alpha x, and this is known as the transmitted. Transmitted. The probability of incident is mod a square. The probability of reflecting wave mod b square. The probability of transmitted, it is a non-zero probability. It is known as mod x square, right? This is mod x square. Xi 3 of x, this is xi 1 of x, right? So we have to just calculate for the region 2. We have to calculate for region 2. Now let's calculate for the region 2. Okay. For region 2, what is written? We consider E less than V naught, the classically forbidden condition that the total energy cannot be less than the potential. Okay, but this is quantum mechanically possible. So we can apply the Schrodinger equation minus h cut square 2m del square xi as a function of x into del x square equal to, we can write that E minus V naught into xi of x. So del square xi as a function of x upon del x square equal to, we can apply V naught minus E into 2m upon h cut square into xi of x. Absolutely. So now let's apply beta square. So this is beta square equal to 2m into V naught minus of E upon h cut square, right? This is beta square. Now from this we can write that d equal to plus minus of beta. So in the second region, xi as a function of x is known as c e to the power alpha x, sorry, c e to the power beta x plus d e to the power minus of beta x, right? Right? Okay. Now we have three wave functions for 1, 2, and 3. We have three wave functions, right? Now applying the boundary conditions. Now apply the boundary conditions for applying the boundary conditions, right? Applying the boundary conditions. So at x equal to 0, boundary means x equal to 0 and x equal to L. There are two boundaries are there. So for xi1 at x equal to 0 equal to xi2 at x equal to 0. This xi1 is composed of these two wave functions, right? And this is known as f e to the power ix, right? So xi1 at x equal to 0 equal to xi2 at x equal to 0. And of course del xi at x equal to 0 upon del x at x equal to 0 equal to del xi2 at x equal to 0. They both are equal. So from this first condition we can write that a plus b equal to c plus d. E to the power alpha, this is 0, this is 0, c plus d will be there. And second is a minus b equal to beta by I alpha into c minus d. And the second boundary condition at x equal to L, the second boundary conditions xi2 at x equal to L equal to xi of 3 at x equal to L. And of course the differentiation d xi2 upon del x at x equal to L equal to d xi3 of dx at x equal to L will be equal. So c e to the power beta L plus d e to the power minus of beta L equal to f of e to the power I alpha L, right? And another is e to the power beta L c minus of d e to the power minus of beta L equal to I alpha by beta into f e to the power I alpha L. Okay. So let condition, this is 1, this is 2, and this is 3, this is 4. There are 4 equations are there. Just speed up your writing because you don't have so much time for these calculations. Now we have this 4th equation, right? So there are 2 things I have to calculate. We especially are interested in the transmittance. Transmittance means J in transmitted, the probability current density of the transmitted upon incident, right? This is H cut of N, the imaginary part of xi star of del of xi, which is transmitted. And this is H cut of M, this is imaginary part of xi incident star of del of xi I. Okay. So in both these the coefficient is alpha, right? So you can directly write is mod x square upon mod a square. There is no problem because xi star equal to take only one calculation. This is a to the power alpha x, right? So this is a to the power alpha x. This is xi transmitted as a function of x. We know. So del of xi t as a function of x with respect to the function of x I alpha a to the power alpha x, and xi t of the star as a function of x equal to I alpha f into e to the power minus of I alpha x. If we multiply this, so imaginary part of xi star of t as a function of x and to del of xi t as a function of x is this alpha into mod h square, right? Alpha into mod h square. And for this region, alpha into mod of a square. So alpha cancel, mod h square upon mod a square. This is all our physics basics. We are not here to talk about all this stuff. So we are interested on this. So if we solve all the equations, okay, of this 1, 2, and 3, 4 equations, right? We will get the transmittance is, okay, solving all 4 equations. Solving of this is all mathematics. The transmittance is actually 1 plus alpha square plus beta square upon 4 alpha square beta square into sine hyperbolic functions square of beta L whole to the power minus 1, correct? So we can write 1 plus, if we apply this alpha and beta, the alpha square equal to 2m upon h cut square and the beta square equal to 2m into v naught minus of a upon h cut square. If this add, if we add, the e will be cancelled. This is 2m and 4 beta 4 v naught square, right? Yeah, 2m v naught and alpha equal to this. So we can write is v naught square into 4e into v naught minus of e into sine of h square of beta whole to the power minus 1. Now there is a limiting case. This is very important to discuss. This is the transmission coefficient. This T is the transmittance or transmittance coefficient. So we can write that if there is a L greater than 0, L is very large and this E is very less than V naught. So we have applied very small energy, okay, very small energy compared to the potential energy, right? So we can write approximately, if this case happens, so the transmittance, what will be this? 1 plus this sine h equal to e to the power beta L minus e to the power minus of beta L upon 2. So we can write that is V naught square. L is very large, right? So e to the power 2 of beta L upon 16 of E into V naught minus of E whole to the power minus 1, right? Right, whole to the power minus 1. If this limiting condition is there, okay, if this limiting condition is there, so we can write it. So this is very much large. Why? Because T equal to, this is 1 plus V naught square upon E square into 16 of V naught by E minus of 1 and e to the power 2 beta L whole to the power minus 1. Now V naught by E is very much than 1. So this is very much large, right? If this is very much large, we can ignore this plus 1. We can ignore this plus 1, right? So we can write it 16 into E into V naught minus of E to the power minus of 2 beta L. If this ignore 1, so this will be whole to the power minus 1. So we can flip 16E into V naught minus E upon V naught square. This is transmittance equal to 16E V naught minus E upon V naught square e to the power minus 2 beta. This is constant. This is the constant which is known as the prefactor. And this is known as the exponential. So this thing is actually supposed to note. So we can approximately write e to the power minus of 2 beta L is the transmittance, right? Okay, this is beta, right? This is beta. And what is the beta equal to? 1 by h cut square root of 2m into v minus of e. This is beta. And in this case, the v is constant. In many cases, the v cannot be constant. So T equal to transmittance equal to e to the power minus of 2 beta L and beta equal to 1 by h cut square root of 2m v minus of e. This is a prefactor. We can write through this approximation. If this L is very large, we can write e to the power minus of 2 beta L. Okay, this is prefactor. If we consider v naught by e square, v naught by e minus 1, so this is reduced to plus 1. Okay, for this condition. If we apply this condition, the T can write e to the power minus of 2 beta L, and where beta is this for the constant potential. Okay. So do all the mathematical calculations which I have skipped. So why we have to calculate? So why we have to calculate this? So why we have to calculate this? First of all, we have to calculate beta, right? Okay, so this is all about quantum tunneling. We have done some approximate calculations. We have understood what is actually quantum tunneling effect. If you like this description, if you like this video, please do share with others. Please subscribe the channel. And if you have any doubts, please let me know in the comment section. Jai Hind, Tata.